Black holes, one of the most baffling and peculiar phenomena in the universe, remain a subject of extraordinary review and interest among space experts and physicists alike. These celestial objects, defined by their monstrous gravitational pull and the total absence of light emission, represent a limit beyond which the known laws of physical science no longer apply. First speculated by Albert Einstein in 1916 as a consequence of his theory of general relativity, black holes were only theoretical until technological advancements allowed for their indirect detection during the 20th century. The turning point came during the 1960s, when researchers studying the Cygnes group of stars accidentally discovered an unusual celestial object, a brilliant blue star emitting high-energy X-rays. This star, orbiting an invisible companion, defied regular explanations until it was revealed to be in a gravitational relationship with a massive black hole, Cygnes X1. The discovery of Cygnes X1 provided clear evidence for the existence of black holes and marked the beginning of a new era of investigation into these cosmic enigmas. Cygnes X1, located about 6,000 light-years away from Earth, is extremely dense and possesses such a powerful gravitational force that not even light can escape its grasp. This defining feature earned it the name black hole, which holds the essence of these mysterious objects. Subsequent research has uncovered a variety of black holes scattered throughout the universe, with estimates indicating that the Milky Way alone may harbor more than 100 million black holes. Despite their size and elusive nature, direct detection remains challenging. Astronomers have identified a number of candidates from our galaxy, ranging from stellar mass black holes formed from the remnants of massive stars to supermassive black holes located at the centers of galaxies. The gravitational influence of black holes extends far beyond their immediate vicinity, influencing the course of cosmic structures and affecting the fate of surrounding matter. Objects that venture too close to a black hole face a fate determined by its relentless force. They are drawn inevitably toward the event horizon, the final boundary, where they are subjected to extreme tidal forces and ultimately consumed by the singularity at the black hole's core. This catastrophic interaction, known as spaghettification, is the extreme manifestation of a black hole's gravitational strength. As an object approaches the event horizon, the gravitational gradient across its length becomes stretched to its extremeness, contorting into a filamentary shape resembling strands of spaghetti. The forces exerted by the black hole overpower the internal bonds keeping the object intact, causing it to disintegrate into a stream of matter that eventually merges with the singularity. Despite the allure of black holes as laboratories for testing the limits of physical theory, they remain shrouded in intrigue. The quest to unravel their secrets persists, motivated by a desire to understand the fundamental nature of space-time and gravity itself. In the vastness of the universe, black holes stand as silent sentinels, beckoning humanity to explore the depths of the unknown and expand the boundaries of human knowledge. Despite the tremendous distance separating us from the nearest black hole, approximately 1,500 light-years away, questions and concerns about their potential impact persist. In 2021, researchers achieved a monumental breakthrough by capturing the first clear image of a black hole, specifically M87, located at the center of the M87 galaxy. This remarkable achievement provided crucial insights into the nature of black holes and their elusive structure. The visual data revealed that black holes have complex layers, challenging the traditional perception of them as solitary entities of pure nothingness. Through meticulous analysis and imaging stitching, scientists identified 3 distinct layers within a black hole. At the outermost layer lies the event horizon, a critical boundary marking the point of no return. Once an object crosses this threshold, gravitational forces become insurmountable, ensuring its inevitable fall into the black hole's depths. Moving inward, the photon sphere constitutes the second layer, where light orbits the black hole in perpetual captivity. Any photons that venture into this realm succumb to the overwhelming gravitational pull, trapped forever within the cosmic embrace of the black hole. At the heart of the black hole lies the singularity, the third and final layer, where the laws of physics break down. The familiar laws governing the universe cease to apply, plunging researchers into a place of extreme unpredictability and theoretical speculation. The complexity of black holes and their inherent challenges to our understanding is significant. While they share a common 3-layer structure, each black hole exhibits unique characteristics and behaviors, defying simple categorization. As such, traditional methods of scientific inquiry prove insufficient for studying these cosmic behemoths, necessitating innovative approaches to unravel their mysteries. Indirect observation remains the primary means of studying black holes, as direct investigation is made impossible by the enormous barriers posed by their gravitational forces. Attempts to launch probes into black holes would inevitably result in their destruction, crushed into obscurity by the relentless forces at play. Nevertheless, researchers persist in their quest to decipher the secrets of these cosmic giants. Various theories, ranging from stellar collapse to cosmic dynamics, offer tantalizing glimpses into their behavior and origins. In particular, NASA's study of the cosmic center of M87 revealed compelling evidence of a supermassive black hole exerting its gravitational influence over vast cosmic scales. Despite these difficulties, the pursuit of knowledge continues unabated, driven by humanity's inherent curiosity and thirst for understanding. While the enigma of black holes may elude simple comprehension, the steadfast dedication to scientific inquiry promises to illuminate the darkest corners of the universe, revealing its deepest secrets hidden within. Roy Kerr's groundbreaking work in 1963 presented a paradigm-shifting perspective on black holes, presenting an innovative theory of rotating black holes that defied conventional understandings. Central to Kerr's model was the concept of the ergosphere, a region surrounding the black hole where divergent forces balance gravitational collapse, preventing matter from collapsing further inward. This novel domain displayed curious deviations from traditional physics, hinting at the profound mysteries concealed within black holes. However, the most fascinating aspect of Kerr's theory was the prediction of an Einstein-Rosen bridge, informally known as a wormhole. This hypothetical structure represents a possible entry point through spacetime, offering a conduit between distant regions of the universe or even parallel universes. The idea of wormholes stems from the intricate interplay between reality as described by Einstein's theory of general relativity. In this framework, existence is woven together, forming a four-dimensional fabric known as spacetime. Massive objects warp this fabric, creating gravitational fields that influence the motion of surrounding material. Wormholes essentially act as shortcuts through this cosmic fabric, connecting distant points in spacetime and potentially enabling rapid traversal. In addition to theoretical limitations, energy requirements for maintaining a stable wormhole are astronomical. Scientists hypothesize that exotic matter with negative energy density might be necessary to keep a wormhole open. However, such matter has not yet been observed in nature, and its properties remain purely speculative. Without a feasible method to produce or stabilize this exotic matter, the dream of traversable wormholes remains confined to the realm of theory and science fiction. Yet, black holes, and the theoretical possibilities they inspire, continue to drive some of the most cutting-edge research in physics. Quantum mechanics, which governs the behavior of particles at the smallest scales, often conflicts with general relativity, which describes gravity on cosmic scales. Black holes sit at the intersection of these two foundational theories. The singularity at a black hole's core, where density becomes infinite and space and time cease to have conventional meaning, is perhaps the most extreme arena where this conflict plays out. This has prompted physicists to seek a unified framework, a theory of quantum gravity, that could reconcile these divergent models. Among the leading candidates is string theory, which suggests that all particles and forces arise from vibrations of tiny one-dimensional strings. Others explore loop quantum gravity, a theory that quantizes space itself. Both approaches attempt to describe the fabric of the universe at its most fundamental level, where black holes may offer critical clues. The information paradox, famously posed by Stephen Hawking, is one such puzzle. According to quantum mechanics, information cannot be destroyed. Yet, when matter falls into a black hole, it appears to vanish entirely, seemingly erasing any trace of its origin. This contradiction has led to intense debate. Recent theoretical developments suggest that black holes may actually encode information on their event horizons, a concept known as the holographic principle. If proven, this could revolutionize our understanding of the universe, suggesting that the three-dimensional world we observe is a projection of data stored on a two-dimensional surface. The study of black holes is not merely an abstract exercise. As our observational capabilities expand, so does our ability to witness the dynamic role black holes play in shaping the universe. Using advanced instruments like the Event Horizon Telescope and gravitational wave detectors such as LIGO and Virgo, scientists have observed black hole mergers, cataclysmic events that release unimaginable amounts of energy and ripple through spacetime itself. These discoveries not only confirm Einstein's predictions but also offer new insights into the birth and evolution of galaxies. Moreover, black holes are increasingly recognized as cosmic engines that regulate galactic ecosystems. Supermassive black holes, millions to billions of times the mass of our Sun, reside at the centers of most galaxies, including our own Milky Way. Their powerful gravitational fields influence star formation, galactic structure, and even the chemical evolution of interstellar matter. Far from being merely destructive, black holes play a crucial role in maintaining the cosmic balance. As we venture further into this century, the frontiers of black hole research promise to deepen our grasp of reality itself. They challenge us to rethink space, time, matter, and the very nature of existence. In their silent, lightless depths lie the keys to understanding both the smallest building blocks of the universe and the vast cosmic web that binds galaxies together. Black holes remain both a scientific enigma and a philosophical mirror, reflecting the limits of what we know and the boundless scope of human curiosity. They remind us that the universe is far stranger and more wondrous than we can imagine, and that our quest for knowledge is only just beginning. Wormholes existed. They might not help as quickly as light travel, a cornerstone of many sci-fi narratives. Despite these challenges, the allure of wormholes endures as a beacon of scientific interest and exploration. The concept of the wormhole, named by its pioneer scholar, embodies the tantalizing promise of cosmic portals and alternate facts that call humanity to contemplate the mysteries of the universe and ponder the infinite possibilities that lie beyond. The quest for a unified theory that reconciles the seemingly disparate domains of gravity and quantum mechanics has spurred the search for an explanation for everything, a comprehensive framework capable of bringing together all of the fundamental forces and particles in the universe. At the forefront of this endeavor stands renowned theoretical physicist Myoku, whose groundbreaking work has propelled the study of superstring theory. Superstring theory represents a dramatic departure from conventional ideal models, hypothesizing that fundamental particles are not point-like entities but rather microscopic vibrating strings. These strings, much like the strings of a musical instrument, resonate at specific frequencies, giving rise to the various particles and forces observed in nature. In this paradigm, the universe becomes akin to a grand symphony, with each particle corresponding to a distinct harmonic resonance of these fundamental strings. One of the most striking implications of superstring theory lies in its potential to explain mysterious phenomena associated with black holes, wormholes, and other exotic solutions to Einstein's equations of gravity. As strings traverse the fabric of spacetime, their dynamic motion leads to the formation of gravitational singularities and topological anomalies. Whereas superstring theory's elegance masks its inherent complexity, it necessitates the existence of additional dimensions beyond the familiar three spatial dimensions and one temporal dimension. These extra dimensions, hidden from direct observation, present a significant challenge to human intuition. Nevertheless, applied models, such as the analogy of fish living in a two-dimensional lake, provide a glimpse into the elusive nature of these higher dimensional realms. The compactification of these extra dimensions, akin to folding a rolled-up piece of paper, renders them imperceptible at everyday scales. Yet their influence permeates the very fabric of reality. While the precise nature of these hidden dimensions remains elusive, their theoretical presence offers a promising explanation for the complex structures and anomalies observed throughout the universe. The mathematical foundations of superstring theory have sparked a renaissance in mathematical physics, revealing profound connections between dynamic mathematical patterns and physical phenomena. In fact, the search for a theory of everything has catalyzed the union of disciplines, shedding light on the deep interplay between mathematics and the natural sciences. Despite its theoretical elegance and scientific potential, superstring theory remains an untested framework, awaiting experimental confirmation. The elusive nature of additional dimensions presents a formidable barrier to experimental verification, relegating superstring theory to the realm of mathematical speculation. Nevertheless, the audacious vision of superstring theory continues to captivate the minds of researchers and enthusiasts alike, enticing humanity to embark on a journey of intellectual discovery and exploration. As we venture deeper into the known domains of theoretical physics, guided by the illuminating beacon of superstring theory, we confront the vast mysteries of the universe, poised on the threshold of a new era of understanding and enlightenment. The task of unraveling the secrets of quantum black holes has long perplexed physicists, representing a monumental challenge to our understanding of the fundamental nature of the universe. Despite numerous efforts to tackle this riddle, the live solution has remained beyond our grasp, prompting Edward Witten, from the Institute for Advanced Study at Princeton, to describe superstring theory as 21st-century physics that ended up by accident in the 20th century. However, recent advancements have injected new hope into the quest for comprehension of quantum black holes. Several groups of physicists have independently reported a significant breakthrough, revealing that string theory could offer a comprehensive solution to the problem, albeit within the more constrained context of 2 dimensions rather than the full 10-dimensional framework set forth by conventional superstring theory. While this represents a promising step forward, the quest for a complete resolution remains ongoing. The complexities of the situation present significant hindrances. The search for a single theory of everything beckons us to probe the deepest recesses of cosmic existence, where the boundaries between reality and theory blur and the secrets of the universe await discovery. The study of black holes carries profound repercussions for our comprehension of the universe, challenging our notions of reality and raising questions about the nature of existence itself. The interplay between black holes and other astronomical phenomena, such as neutron stars and gamma bursts, reveals the intricate processes at work in the cosmos. These cosmic interactions not only challenge the limits of our current understanding but also offer invaluable clues to the underlying architecture of the universe. Black holes, once considered mere theoretical oddities, have emerged as critical laboratories for testing the limits of physical law. Their extreme environments, where space-time curvature becomes immense and quantum effects dominate, present a rare opportunity to unify general relativity with quantum mechanics. Recent observations, such as gravitational waves resulting from black hole mergers and the historic imaging of a black hole's event horizon, have further invigorated scientific interest. These milestones, achieved through instruments like LIGO and the Event Horizon Telescope, have transformed speculative ideas into measurable phenomena. They offer hope that even the most abstract components of string theory may one day be accessible to empirical inquiry. Parallel to these developments, physicists are exploring holographic principles, which suggest that our universe might be fundamentally described not by a volume of space, but by information encoded on a lower dimensional boundary. This radical concept, born from the study of black hole entropy and advanced through the ADS-CFT correspondence in string theory, has reshaped foundational perspectives on spacetime, gravity, and information. If proven correct, the holographic principle could reconcile contradictions between relativity and quantum theory, proposing a vision of the universe where three-dimensional reality emerges from a more fundamental, two-dimensional framework. Such ideas not only redefine the nature of physical existence but also touch on philosophical questions that have occupied thinkers for millennia. What is reality? What is the true nature of space and time? As these investigations progress, they underscore the indispensable role of imagination in scientific discovery. Theoretical physics, for all its mathematical rigor, thrives on bold ideas, on daring to ask questions that reach beyond the observable into realms that challenge the very fabric of reason. In this spirit, superstring theory and its descendants remain vital, not merely for the answers they may one day provide, but for the new questions they inspire. The pursuit of a theory of everything is not just a scientific journey, it is a human one, a voyage driven by curiosity, wonder, and the desire to understand our place in the cosmos. In bridging the smallest scales of quantum fluctuations with the largest structures of spacetime, physicists strive to construct a coherent picture of reality, one in which the mysteries of the universe no longer stand as impenetrable enigmas, but as luminous gateways to knowledge, insight, and awe.